Hello everyone. So in this particular video, we are going to see the next question that is related to the restricted earth fault relay. So if I talk about the restricted earth fault relay, it is used in alternator and transformer against earth fault protections. Okay, so I will discuss about this protection scheme for alternator and transformers, how things are working, and why this restricted word is used in case of restricted earth fault relay. Okay, so let me consider alternator first. Let's say this is your alternator, and this is the neutral point of the alternator. Okay, and basically neutral point of alternator is grounded through a resistance. We use resistance grounding in case of alternator. There is a reason for that. This resistance grounding basically increase the or improve the stability of the system, or sometimes this resistance also limit the fault current if there is any single line to ground fault and all. Okay, now let's say this is your alternator, and you want to protect the windings against any kind of earth fault. So earth fault like winding can touch the ground and there can be fault. So we should be able to detect this particular fault and all. Okay, and the name suggested it is saying the restrict earth fault relay. So this particular operation will be you can say restricted to the protection zone only. So if I'm calling this is my protection zone, so let's say this one is my protection zone. Okay, so if anything happens outside this protection zone, my this restricted earth fault relay will not operate. So it is my protection zone, you can say. Okay, and how things will work, I will explain now. So let's say I have CT here, current transformers, and they are connected in this fashion. Let's say, okay, and these are the three cities, you can say, and these are the cities is used to measure the currents, and depending on these currents the relay coil will be energized, and relay will send the trip signal to circuit breaker, and it will trip. Now these are the cities, and we also have one more city that is connected to this neutral. Okay, so let me erase this portion. So let's say I have this city terminals. Okay, and basically I'll be having relay coils here. Let me connect these 2 points. So let's say I have connected these 2 points, and this is my, let's say, relay coil. Okay, and these relay coils are connected in this way, and there will be this relay coil will be energized, and it will send that trip signal to circuit breaker, and it will trip like that. Okay, now the thing is why there is need of these four CTs. Okay, these are the CTs, right? So CT. So if I call it as a CT1, CT2, CT3, and CT4. So this is the current transformers. Now let's say you got a fault at this point. That is, this fault location is not comes under the protection zones. Okay. So in that case, what will happen? Let's say current IA, IB, IC was flowing. Let's say A phase, B phase, and C phase, and IA current was flowing, IB current was flowing, and IC current was flowing. Now, the moment you got a fault, this fault current will complete its path through this neutral resistance, you can say. And the moment you are getting fault that is not located in the protection zone, the IA, IB, and IC will not be a balanced current. There will be imbalance comes into picture, right? And whenever there is an imbalance in this phase currents or voltage, whatever it is, according to Fortescue theorem, you can split this unbalanced three quantities into two balanced quantity and one co-phasal quantity, you can say. So there will be positive sequence quantity, negative sequence quantity, and zero sequence quantity, you can say. And this neutral this IA, IB, IC is back is you can say it is Also the summation is equals to the neutral current. So basically the IN, if I am calling this IN is a neutral current, so IN is coming here, and IA, IB, IC is splitting in three paths. So if I write the neutral current, IN is equals to IA plus IB plus IC. So this current now has imbalance, and because of that the positive sequence component and negative sequence components will be like vanished, and you will be having only zero sequence component of current. So that component will be 3 times of Ia naught. Okay, I hope you know these things, like what is symmetrical component theorem, that is it is coming from there. So I'm not going to the detail, but I am only interested in this particular quantity, zero sequence component of current. Now the moment you got a fault, let's say that I'm calling this fault point as F2. Okay, so at F2 fault point, what is happening basically? This current IA, IB, IC is imbalance, and so the reflection that will come into the CT secondary, let's say this is the reflection currents. So this is the reflection currents and reflection currents. So if you take summation here, so the I'm calling it as, let's say, IA prime plus IB prime plus IC prime, and this current will also contain the imbalance, so that will have a 3 times of IA naught prime. Okay, so this will be the current at the secondary side of the cities, and at the same time I am having the currents like at the neutral also. So this neutral current is basically equals to 3 times of IA naught. If you take the reflection the secondary side of this particular CT4, you will be having current 3 IA naught only, 3 IA naught, IA naught prime, sorry, 3 IA naught prime. So you can see this 3 IA naught prime current is basically, it is coming from the neutral reflection also, and basically it is completing the path within the cities. It is not even going into the operating coils. Okay, it is not even going into the operating coils. So what will happen, your operating coil will not be energized, and your operating coil will not send any trip signal to circuit breaker. So that means if any fault occurs that is not located in the protection zones, let's this fault F2 point is not lies in the protection zone, then your the third harmonic, so not third harmonic, it is the zero sequence component of current or zero sequence current is only flowing through the CTs. It is not coming to the operating coil. So that's why the F2 fault will not be detected. And now we will see if the fault occurs inside the protection zone, then what will happen, that we will observe. Okay. Now let me erase these things. Let me erase these things also. Okay. So F fault at F2 point will not be detected. Okay. So hmm. Now let's say fault has occurred uh, at this particular point. Let's say this call, I'm calling this as a F1 point. At F1 point, what is happening, that we are going to analyze. Now fault has occurred at F1 point. Now this fault current will return through this neutral wire, you can say. Okay, now what will happen, like you can see, basically the neutral current will be, I can write the neutral current will be equals to the fault current, and this is my fault current. Okay, IF. Okay, now you have a winding, you got a fault here. So if the voltage in the winding, like the in the during healthy condition, if the healthy phase was producing voltage, let's say E at an angle 0, okay, because of the location, depending on the location, that voltage will simply get split into two part. Like here, maybe it will be some percentage of the E, maybe it is XE, Xc at an angle 0 volt will get induced, and 1 minus X E at an angle of 0 voltage will get induced in the coil. So depending on the fault location, the voltage will get split, but total voltage will still remain the same. Like, okay, the total voltage will still remain the same, and there will be no impact in the, you can say, the current IA, IB, IC. So this current will still be a you can say it will be balanced current, because uh, my this IA, IB, IC, if you look from this point, this terminal, you can say my source voltage is fixed, but fault has occurred inside, okay, and this fault resistance or resistance of the fault path is 0. So the current that was coming before the fault and after the fault, you can say, it will be balanced, so it will be the same current, you can say. So if I just talk about the reflection of this IA, IB, IC current here, it is a balanced current, right? So if it is a balanced and it is a so if you split this particular quantity, so it is itself a positive sequence quantity, right? So the phasor summation of this IA, IB, IC at this phasor at this particular terminal, it will be 0 ampere. Okay, since this IA, IB, IC are balanced, so the reflection that will come into the secondary side of the summation, so it will be 0 ampere. But my fault current is flowing through this neutral path, and that is not that is not 0, because depending on this XE voltage, XE at an angle 0 voltage, and depending on this neutral resistance R, some current will flow, and if anyhow that current is more than the pickup current of the relay, and basically that current will flow to the secondary circuit also, and that will come, and 0 current is flowing here. So that current will come now the relay operating coil, and it will complete its path, and your operating coil relay will send a trip signal to circuit breaker, and it will trip, and it will detect the fault in the protection zone. So this is how your protection of the restricted arc fault relay is restricted to the protection zones only. So that's why we call it as a protection, restricted arc fault relay. And basically, depending on this R value, you can protect your alternator windings basically against the earth fault. And unfortunately, due to this R, you will not be able to protect your 100% of the winding. There will be some around 80 to 85%, or even sometime 90% of the winding can be protected by using this restricted arc fault relay. Because of this R, basically you cannot fully protect your winding. So what can happen? Let's say because of this internal fault, you are getting some current I is equals to X E by R. Okay, and if you see the CT secondary current, let's say I'm calling CT secondary current. Obviously, this is the fourth number CT. So this CT4, the reflection current may be the current I'm getting. If it is the less than the pickup current of this particular operating coil, if that current is less than the pickup current, that my relay will not operate. So you can say up to some point, like around 80 to 85% winding only it can be protected. Beyond that, you cannot protect because of this resistance. Okay, so this is the scenario for alternator winding protection. It is star connected alternator winding, so same thing will happen with the star connected transformer also. In that case, like in transformers, basically we prefer to have solid grounding. So in that case, you can go this protections up to nearly about 100%. So now I'm going to consider the delta connected windings. Maybe let's say I have a delta connected system. Let's say I'm considering this is a transformer, for example. This is a transformer, and it has some secondary circuit. Okay, I'm not drawing that. Now I have three CTs. have Three CTs. Okay, now let's say this is my operating coil. Okay, so this is my operating coil, and it will send a trip signal to circuit breaker. You can say that this is my operating coil. Okay, and basically this is my protection zone. Now let's say fault has occurred at this terminal, then what will happen that we are going to analyze here. Now, basically, if any fault has occurred, maybe I should take one source also, then it will be easy to explain. Mm, Here's this thing. I can take a source combination. Let's say I have a star connected source and the source of neutral of the source is grounded, and these are the windings, let's say. Okay. And I'm not showing the secondary circuit. Okay. I have the CTs here, CT secondaries are connected, and let's say this is my operating coil, relay operating coil. Okay. And this is the, you can say it will send the trip signal to circuit breaker. Now, and also this is my protection zones. Okay. Anything happens that is not comes under this protection zone, it shouldn't, the relay should not send the trip signal. Now let's say you got a fault here outside the zones. Okay, now what will happen? See, this is your delta connected system. So the current that is flowing here, here, let's say it is IA, it is IB, and it is IC. So the currents are the IIBIC is flowing through the, you can say, lines, but you got a fault here. Okay. Now this particular fault current will complete its path through this particular path. Basically it will come, it will go. Okay, you may think okay, it is short circuit, but I'm not showing the, you can say, the source impedances and all, but it will not be short circuited. There will be lines, resistance, line impedances and all, but as of now I'm just neglecting that, all of this resistance and impedances and all. Okay, but the fault current will complete its path through this neutral, you can say. But in case if you think from the delta circuit point of view, in delta there is nothing like neutral and all. Okay, so IA, IB, IC should be 0. IA plus IB plus IC should be equals to 0, right? This should be equal to 0. So even if the fault has occurred here, the imbalance may come into IA, IB, IC, but there will not be any zero sequence component of current. Why? Because zero sequence current are always in cophasal. Okay, so that cannot be like that summation actually cannot be 0. So the zero sequence component of current cannot flow in the delta winding, you can say, here, and at least in the lines. So what will happen? The summation or the reflection that is coming in the secondary of the CT, this three summation, it will be 0 ampere, and your relay coil or relay operating coil will not be energized, and that will not send any trip signal. But now, for example, the fault has occurred inside the protection zone. Okay. Now let's say fault has occurred inside the protection zone. Let's say you got a fault inside the protection zones. Now this fault current can complete its path from this source neutral. Okay. Now the current that is flowing inside through this line IA, IB, and IC can contain the zero sequence component of current. Why? Because now there is a return path. So obviously my zero sequence component of current flow. So my neutral current that and this fault current will basically simply equals to neutral current. I neutral is equals to IF, and it will be 3 times of IA naught. So the reflection that will come into these three CTs, the summation, if you take the three summation of these currents, okay, the summation, it will be 3 IA naught prime. Okay, so the reflection of this of this current in the secondary, and this current, if this current is more than the pickup current of this relay, then the relay will send the trip signal. So you can see your operations of this relay is restricted to the protection zones only. So that's how we call it as a restricted earth fault relay, and we can protect that the you can say again our windings again earth fault. Okay, this was explanation for star connected system, and this was explanation for delta connected system. Okay, but still if you have any doubt, you can ask me in the chat box. Thank you.